This class is all about modeling real systems. And despite the fact that this course is not focused on modeling systems, there's going to be many times throughout this course I'm going to give you a mathematical model and say, design a controller for this. And you're going to think in the back of your mind, well, where did this come from? Because it's coming out of nowhere. And so I want to spend one class building up your intuition on how exactly we come to get models that we might use for control. So again, this is not the point of the course, but it does give you lots and lots of important insight about where these models come from, how certain terms appear in the models that we will use, and these all have very important consequences when we come to controlling that system. So this is really building an appreciation for that. And so this first bit of first two slides here is really understanding where modeling fits within the whole paradigm of controlling a system. And so we kind of break this down into the real world and the mathematical world, and that's this big barrier that we have between here. And despite the fact that we live mostly on the right-hand side in this course, ultimately what we want to achieve is we want to achieve impact in the real world. And so what we want to avoid is simply staying in the real world and choosing some sort of best guess or hacking approach. And the problem with this is that these kind of approaches don't come with any guarantees. So the idea of going through a more systematic and mathematically rigorous approach is the fact that we can build out guarantees on how well our design will work. And what's also important is the fact that best guess and hacking is essentially limited to our kind of creative understanding about the system. And so when we go through a more mathematical approach, we can rely on the mathematics to bring out things that we don't already have intuition for. And so much more complicated and much more nuanced solutions can come out of this. So the challenge with modeling, though, is that anything that we do to jump from the real world into a mathematical model is necessarily some sort of an abstraction. There's going to be some aspects about the physical system, the real system, that is not captured in the model. And these could be small things that aren't so important, or they could actually be relatively major things that are important, but are just too complicated to take into account. So there's various different models. So oftentimes we'll be talking about multiple different models that we might use. We might use different models for different purposes. So the same system may have different models depending on how you need to use them. But the idea is that once we have this mathematical representation, which is what we're going to call the model, and in this case, a lot of what we're going to be doing, since they're dynamical systems, will be based on differential equation models. So we're going to use those differential equation models and apply, and this is what this course is all about, systematic analysis and design in order to build out controllers that achieve something like what we want to achieve, one of those 4 control goals. And then ultimately we have to take this mathematical approach and apply it back in the real world, where we hope that this works. And this arrow right here underscores the fact that these robust solutions, so despite the fact that there could be disturbances or there could be inaccuracies between our model and our real system, that the design that we have chosen still works. So again, this is a very rather wordy slide, but the main key takeaway here is that there's no mathematical model that's going to be perfect, and it's not going to perfectly represent what's going on in the real system. But what's really cool about this approach and the whole idea of modeling things mathematically is the fact that approximate models work actually pretty well. In fact, even simple models are still extremely useful. And it's this notion of robustness that brings home this usefulness and allows us to use all of this mathematical framework that we're going to talk about in this course in order to solve real problems, despite the fact that the problems that we're solving are actually more complicated than what we're modeling. And part of key to all of this robustness, and this isn't going to be, we're going to take a break and we're going to come back to this in a couple of weeks when we finally start talking about feedback. But the idea here is that feedback is one of the main mechanisms by which we're actually able to give robustness to a dynamical system. And so that's ultimately what we want to achieve with our controller design. So we're going to talk about primarily one way of accomplishing or obtaining models, and that's using first principle approaches. And so these should be things that slightly jog some memories from past classes, whether it's physics or chemistry or an electrical engineering course. But obtaining models can largely happen either through first principle models or through data-driven techniques. And data-driven techniques are ones that are gaining lots and lots of popularity, and there is lots and lots of applications where it becomes useful. One of the challenges, especially for control, is that data-driven models sometimes make it more difficult to apply some of our mathematical techniques. But there is a large literature, even within control theory, largely called systems identification. And that is really what's used in taking data, or essentially data about the trajectories of the system over lots and lots of time, and inferring dynamics that represent essentially, remember, the dynamics are the rules that describe how a system operates. And so in this course, we won't talk a lot about data-driven models. It's kind of a whole course by itself. Here, what we're going to do is we're going to just focus on identifying how first principle models can allow us to create dynamic systems, essentially identifying the laws by which these systems behave. And so these fundamentally are things like laws of physics and chemistry, stoichiometry, and so on. In order to apply these, we often do have to make some sort of simplifying assumptions. Sometimes we can add some more complicated terms, but oftentimes we do assume away some of them. And ultimately what this yields is some set of differential equations, and typically they're coupled, which means that variables in one differential equation appear in another one, so we can't solve them independently. So examples of things that we'll use: F equals ma, Newton's first laws. We could even use conservation of momentum. We could use energy and mass balance. We're going to use Kirchhoff's laws that describe circuits. So all of these are examples of fundamental laws that describe the rules by which a physical system operates. And those are the ones that we're going to be able to use in order to write down the mathematical model that we can use. So one of the key messages of this video has been the fact that simple models, or any model, is going to be a simple representation of the real system, but that simple models are still very useful. And so one particular set of models that we will study throughout this course is linear models. And we'll understand a little bit more clearly what linear technically means. But you can imagine that for starters, that a nonlinear dynamical system will have nonlinear terms. It'll have sines and cosines. It'll have x squareds. It'll have other higher order terms, exponentials possibly, whereas linear will not have those terms. And so again, we'll get into a little bit more detail about what that means. But despite the fact that we will talk exclusively about linear models, which is one of the simplest approaches you can use, this is what is used by industry, except for maybe some of the most cutting edge industries. Linear models are kind of the backbone, the workhorse of industry. And it's almost ridiculous how well these models work and our control system designs. It's really remarkable what they're able to accomplish, despite the fact that our models are oftentimes very different from the actual system. So again, we will talk about linear systems. It would be easy to poke holes at that, except for the fact that they work pretty well. There is an exciting large literature on more advanced techniques for nonlinear systems, and one of the key things before you get there is understanding what you do in the context of linear, because everything we do for nonlinear is oftentimes an extension of what we do in this class. So with that, we're going to dive into a number of different examples about how we develop models using these first principle bases, and how we extract a linear model from that, and how that represents a real dynamical system.